NASA Jet Propulsion Labs. And what we're going to do today is look at solar flares and solar telescopes. And I understand this is the super smart class. So who can tell me what energy level the electrons are normally in hydrogen before they get combined with helium? N equals, bring it down a notch. Okay, here we go. Who knows what the closest star is to Earth? Okay, very good. Let's pass these around. These solar glasses, if you fold them, look at the sun, they're very interesting. Okay, and what we do is look through these special telescopes. Who's got a telescope at home? Anybody? Can you hear me back there? Yeah. Can you hear me? Come on, get a little closer. Come on. This is gonna be. Come on. It's gonna be interesting. Come on. Okay. So, who can tell me what type of atom the sun is made of mostly? There's two main ingredients. Anybody know? Hydrogen and helium is correct. Okay, the sun and every star out there is a factory that combines smaller atoms into larger atoms. Okay, and in that process of helium being combined, it's called the proton-proton cycle. Anybody ever heard of that? No? Well, I'm gonna tell you right now. Okay, proton-proton cycle. It's two hydrogen atoms. Hydrogen is one proton, right, and one electron normally. So hydrogen combines under massive pressure and heat for stars like that one, and it forms the next element up, which is helium. There you go, helium. And when that, did you get that part? Oh, you know this. Turn this way. So it forms helium, and in that process, does anybody know what's released in that process? A lot of energy. Can everybody feel the sun on the side of their face right now? Yeah. Or on their arm, maybe you can feel it a little bit. That's the reaction of that hydrogen combining with helium 93 million miles away. Okay? And in that reaction, what's released are three things really. You end up with a helium atom, okay, a gamma ray, and a photon of light. Okay? So every time hydrogen combines into helium, you get those three byproducts: helium, gamma ray, photon of light. Has anybody ever seen a spectrum of hydrogen burning? You'll get a rainbow color and some black lines going through it. Those are called absorption lines, right? What these telescopes do is they look only at the hydrogen alpha absorption line. Okay, so we're not seeing any other wavelengths of light from the sun. It's just the hydrogen alpha absorption line. It's 656 nanometers. When you look through these telescopes, you're going to see photons that are emitted by hydrogen combining into helium. That may sound complicated, but when you look at it, it's just going to be a red image with some orange peel, okay? And that orange peel is the tops of the hydrogen clouds, the explosions. Just like the bomb, you know, nuclear bomb, you drop somewhere, you get a big mushroom cloud. What you're looking at on the surface of the sun is several billion plasma clouds all at the same time. And the sun also has some flares coming off the sides right now, and there's also a bright area in the center that's called an active region. I need 2 volunteers.
I'll go with you.
I'll speak English. How about the dos volanteros? Okay, good. Here you go. Now, you're going to be my Earth, okay? You're going to be my sun. S-U-N. Okay, so that's an image from the NASA SOHO satellite, okay? Solar Heliospheric Observatory. And it orbits 40 million miles from the sun, about halfway from here to there. And it orbits around the sun and takes pictures of hydrogen alpha. That's what it looks like, okay? Now this, can everybody see this little bitty dot on this piece of paper?
Yes.
Everybody? Yes. How about you in the back? Can you see this little bitty dot? Okay. This is the relative size of the Earth and the sun. We're that size, okay? So it's pretty big. Now I want you to take this Earth, and what we're going to do is show you the relative distance between the two if the sun was this size. So I need you to start walking down the field, and I'll tell you when to stop. Okay?
Bye.
Anybody not get a pair of glasses? Young lady, did you get a pair of glasses?
Yes. Thank you.
Okay. Hang on a minute. Turn around. Now keep going. Who can tell me how long it takes light to get here from the sun? About 8 minutes from this time of year. All right, hold on a minute. Now keep going. Okay. So the light takes 8.5 minutes usually, or somewhere between 8 and 8.5 minutes to get here. So if the sun were to blow up right now, would we feel any effects or see anything right now? Well, nobody really knows. we wouldn't see the light. All right, hang on a minute. Now a little bit further. All right, stop right there. Now hold up to Earth. Now who can see the Earth from here? Anybody? It's pretty tiny, isn't it? Now hold up the sun there, Mr. Sun. That's how far away the Earth is from the sun if the sun were this size. That's a long, long way. Okay, distances in space are enormous. Okay, they always show you on TV where the sun is right there, Earth's going around it, but that's not how it is. Okay, thank you. Now, there's a gravity field, or whatever you want to call it. There's gravity associated with the sun. Would that gravity immediately go away if the sun were to disappear right now, or would it take some time for that effect to be felt by Earth? You know, the only reason Earth is going around the sun is because Earth thinks it's falling in a straight line, but it's falling around the sun, right? That's what causes the orbit. Does anybody know if you feel the effect immediately, or would it take some time for the gravity effect to be felt? Neither does anybody else. Okay, good. So we're expecting you guys to figure that out. I'm too old to think like that now, but all you with your sharp minds, my theory is that as soon as the sun disappeared, the Earth would travel in a straight line out that way. Instantaneously, no time for the effect to take place. Okay, because gravity is not light. Gravity, you know, as Einstein said, it's a warped space, a little funnel. So immediately on the sun disappearing, that would no longer be warped. But I don't know. Everybody else does. Does anybody want to go to Mars? Everybody wants to go to Mars? What if it was free?
This
Want to go to Mars? Yeah, if it was free. Okay. Well, somebody in this age group is going to go because my bosses at NASA are definitely going to have a manned mission to Mars before you guys are as old and decrepit as I am. So the only thing standing between you and going is nothing. It's just a matter of whether you want to or not. Okay. So anyway, who's got a telescope at home again?
Oh, wow.
What happens if you point your telescope at home at the sun and look through it? Anybody know? You immediately go blind. You will probably be killed because it will melt right through your coronary, or right through your cornea, through your rods and cones and into your brain instantaneously. Okay. And that's only if the telescope doesn't melt before you get your eye on it. Okay, because the sun is very, very, very powerful. These telescopes are specially designed just to look at the sun only. You don't see anything else with them. Okay. So they're interferometers inside here. Anybody ever heard of interferometers? You guys are all the advanced class, right? Is this the wrong day? I'm just curious. Okay. Okay, so let's say you're on a boat, and you're, let's say you're standing on a boat, and you got two rocks, and you're on calm seas, okay? And you drop two rocks in the water, about this far away. Waves come out of that, right? Waves are caused by that rock. And what happens to those waves when they come together? Some of them join up, right, and make bigger waves and go out this way. Is that right? Some of them cancel each other out. The troughs meet the high part, they just cancel out. Some of them meet at the troughs and they make bigger waves. Everybody got that? What an interferometer does, which is inside of these scopes, this is an interferometer, there's another one right here. They allow light waves to come in to the telescope. Obviously, put your hand on here, you can see the reflection coming back out. They bounce those light waves between two surfaces, billions of times a second. And what happens is the majority of the waves are canceled out. They go back out the end of the scope. Okay. Only a very, very small portion of visible light is allowed to go through the scope into the eyepiece. Okay. So just like the rocks you dropped, only a small amount get bigger and go out. Most of them are canceled, reflected back. That's what this telescope is. When you go up to the scope, you're going to look in and shade. Put your hand up and shade the sun. Then put your eye right here. Let me get the center of it. Put your eye in as close as you can get it. What you're going to see is a big red ball. And on that big red ball, who's got the sun? You're going to see active regions. There's one like this, and there's a bunch of modeling around the sun. This is called modeling. It's the tops of those hydrogen clouds like we talked about. And on the edge of the sun, you're going to see some flicks of fire coming out. Okay, and those are prominences viewed from the side. When you see them on the surface of the sun, they look like little hydrogen. There's a couple of them there. Okay. So this telescope, and this telescope, and that one, if it's working, they all look at hydrogen alpha light only, so you'll see red images. This telescope looks at the natural color of the sun. If there were any sunspots, we'd see those today, but there aren't any sunspots. So anyway, everybody line up, and try not to grab the eyepiece because you'll knock it off target. But feel free to look through all the scopes as long as you want to.